Memory is one of the most fundamental aspects of human cognition. It allows us to learn, experience, and grow over time, serving as the foundation for our identities and guiding our decisions. But how does our brain retrieve memories? The process of memory retrieval is far more intricate than we often realize, involving complex interactions between different regions of the brain and influenced by both biological and psychological factors. In this exploration of memory retrieval, we will examine how memories are formed, stored, and eventually recalled, shedding light on the science behind remembering and forgetting. The process of remembering starts with encoding, the first step in memory formation. When we experience something new, whether it's a conversation, an event, or a particular sensation, our brain begins to process that information. Sensory input from our environment is translated into electrical signals, which are then processed by various regions of the brain. However, not all experiences make their way into our long-term memory. The brain, as efficient as it is, focuses on processing information it deems important, relevant, or emotionally significant, encoding it for future retrieval. The hippocampus, a small but crucial structure deep within the brain, plays a central role in encoding memories. The hippocampus helps organize the sensory inputs we receive, converting short-term memories into long-term ones. This process can be thought of as the brain saving information in its memory banks, just like saving files on a computer. Once the information is encoded, it moves into long-term memory, which can store vast amounts of information for an extended period, possibly for a lifetime. But what happens when we need to access these memories? How does the brain go from encoding a memory to retrieving it when we need it? Memory retrieval is a dynamic process that involves multiple brain regions working together. Unlike a computer, where files are stored in an organized system, memory retrieval in the brain is more fluid and flexible. The prefrontal cortex, the region responsible for higher cognitive functions such as decision-making, problem-solving, and planning, is heavily involved in memory retrieval. When you attempt to recall something, your brain sends signals to the prefrontal cortex, which then works with other parts of the brain to locate and retrieve the specific memory. The hippocampus continues to play an important role during memory retrieval, especially when it comes to episodic memories, those memories tied to specific events and experiences. However, the retrieval process isn't simply about locating a memory, it also involves reconstructing it. When you recall a memory, your brain doesn't just pull it out of storage in its original form. Instead, your brain reconstructs the memory by piecing together fragments of information stored across various brain regions. This means that every time you recall a memory, it's not a perfect reproduction of the original event, but rather a version influenced by your current emotions, thoughts, and even external cues. The brain retrieves different types of memories in different ways, and understanding this can offer insight into why some memories are easier to recall than others. For instance, memories of events you've experienced, like your first day at school or a recent family gathering, are episodic memories. These memories are highly dependent on the hippocampus, which helps associate sensory details, emotions, and context with the event itself. Other types of memories, such as semantic memories, your general knowledge of the world, are stored in a different part of the brain. These memories don't rely as heavily on the hippocampus, but are stored in the neocortex, the outer layer of the brain involved in higher cognitive processes. When you recall facts, concepts, or general knowledge, your neocortex is activated rather than the hippocampus. Then there's procedural memory, which governs how we perform tasks like riding a bike or typing on a keyboard. Procedural memory is part of what's known as implicit memory, which is different from explicit memory, such as recalling a specific event or fact. Implicit memories don't require conscious thought and are often retrieved automatically without us even realizing it. These types of memories are stored in areas like the basal ganglia and the cerebellum, regions of the brain involved in motor control and coordination. The retrieval of procedural memory is often effortless because it has become deeply ingrained through repetition and practice. The process of memory retrieval is not just about accessing information that has been encoded, it is also influenced by emotions. In fact, emotional experiences tend to create stronger memories that are easier to recall. This is because emotions engage the amygdala, a brain structure closely tied to emotional processing, which works alongside the hippocampus to enhance the strength of memories tied to emotional events. For example, you may have a vivid memory of an event that was particularly joyful, frightening, or sad, and that emotional charge makes the memory stand out. The amygdala's involvement ensures that these emotional memories are encoded and retrieved with greater intensity. In contrast, memories without strong emotional content may fade more easily, which brings us to the concept of forgetting. Forgetting is a natural part of the memory process and occurs for various reasons. One of the primary reasons we forget is due to decay, the gradual fading of memories over time. The more time that passes without accessing a particular memory, the more likely it is that the connection between neurons in the brain will weaken, making retrieval more difficult. This is a normal part of how the brain prioritizes information and ensures that only relevant and frequently accessed memories remain intact. Another reason for forgetting is interference, which occurs when new memories or information interfere with the retrieval of old ones. There are two types of interference: proactive interference and retroactive interference. Proactive interference occurs when older memories interfere with the ability to recall newer ones, while retroactive interference happens when new information disrupts the retrieval of older memories. For example, if you learn a new phone number, it may interfere with your ability to remember an old phone number you've previously memorized. The phenomenon of forgetting can be frustrating, especially when it involves memories you care about. However, just because you can't retrieve a memory immediately doesn't mean it's gone forever. Often, the memory is simply inaccessible at that moment. It might be that the retrieval cues, specific triggers that help activate a memory, aren't available or haven't been activated yet. This is where retrieval cues come into play. Cues can be environmental triggers, such as a familiar smell, sound, or even a particular word, that help activate the brain's retrieval processes. The presence of the right cue can make it easier to access a memory that had previously felt elusive. While memory retrieval can be highly effective and accurate, it's not always perfect. The reconstructive nature of memory means that it's susceptible to distortions. Every time we retrieve a memory, it can be influenced by our emotions, current experiences, or even suggestions from other people. This phenomenon is known as false memory, where we recall events that may not have occurred at all or misremember details of events that did happen. In some cases, suggestions or leading questions can cause our brains to fill in the blanks with false information, leading to the creation of memories that are, in fact, entirely fabricated. As our understanding of memory retrieval evolves, researchers have discovered ways to enhance the process. Techniques such as spaced repetition, which involves reviewing information at gradually increasing intervals, have been shown to improve the retrieval of long-term memories. Additionally, the use of mnemonic devices, like acronyms or rhymes, can help create associations that make it easier to recall information. The key to improving memory retrieval lies in strengthening the neural connections associated with the memory and making sure those connections are activated regularly. Another factor that plays a crucial role in memory retrieval is sleep. Sleep is essential for consolidating memories, transforming short-term memories into long-term ones. During deep sleep, the brain works to reinforce neural connections, improving memory retention and making it easier to recall information the following day. Studies have shown that sleep-deprived individuals tend to struggle with memory retrieval, highlighting the importance of rest in the cognitive process. As we age, the ability to retrieve memories may begin to decline, which is a natural part of the aging process. The hippocampus and other brain regions involved in memory retrieval can become less efficient, leading to difficulties with recalling recent events or new information. In some cases, neurological diseases like Alzheimer's or dementia can cause significant memory loss, severely affecting one's ability to retrieve both recent and long-term memories. Understanding how memory retrieval works is crucial for developing treatments and interventions for these conditions. In conclusion, the process of memory retrieval is a dynamic, multifaceted system that involves various brain regions working together in a highly coordinated manner. From the encoding of information to the reconstruction of memories, retrieval is influenced by factors such as emotion, interference, and time.